Welcome to the latest instalment in our webinar series, Decarbonising New Zealand's Concrete Industry. Jeff Vickers and Tim Kleier discuss the progress that's been made since the launch of the Net Zero Carbon Roadmap in August 2023. They look at key strategies for reducing carbon emissions and how industry-wide efforts can drive sustainability in the concrete supply chain. Let's get into it.
Welcome to today's webinar. Thanks for joining us. Today we're going to be talking about decarbonising New Zealand's concrete industry, progress, challenges and future opportunities. Tim will give you through some of the context of who Concrete New Zealand are, the organisation that put it together. I'll talk through some of the actual kind of findings, some of the levers that we looked at, and the actual kind of outcomes in terms of how we get to a net zero carbon concrete industry in New Zealand by 2050. And then Tim will kind of talk about what's happened since in the year since the roadmap was launched. So with that in mind, I'll hand over to Tim to give us the initial introduction. Over to you, Tim.
Thank you for the kind introduction, Jeff, and a very warm welcome to today's session, also from my side. For those who may not be familiar with Concrete New Zealand, allow me to briefly introduce our organization. Concrete New Zealand is a member-driven industry association committed to advocating for sustainable construction materials. Concrete New Zealand is organized into 5 sector groups, each representing a different segment of the concrete industry: cement, ready-mix, precast, masonry, and reinforcing. In addition, we host a learned society whose members are predominantly structural engineers. Jeff, may I ask you to click one further? Across New Zealand, there are approximately 200 ready-mix concrete plants spanning from Mangunui Haulage Limited in the far north to Firth's plant in Invercargill in the south. All of these plants are part of the Concrete New Zealand's Plant Audit Scheme, an independent program designed to review and ensure that each plant's quality systems meet the requirement of New Zealand Standard 3104, the National Concrete Production Standard. Given the diversity of our audience today, maybe we can switch on to the next slide and taking a moment to highlight the significant contributions concrete makes to our society today. The images you see on these slides are just a small selection showcasing the incredible versatility of concrete and emphasizing its key attributes: durability, water resistance or permeability, depending on your needs, thermal mass, acoustic insulation, fire protection, resilience, cost efficiency, adaptability, reusability, and yes, sustainability. Now, you might be surprised. No, wait, Jeff, one second, still on the other slide. Thank you. Now, you might be surprised to hear that, but it's true. While concrete's embodied emissions per unit are relatively low even, sustainability isn't even solely defined by carbon emissions alone. Many of the features I just mentioned make concrete a highly sustainable choice for the built environment. Where other materials might need frequent maintenance or even replacement, especially in demanding conditions, concrete is built to last. It provides safe, long-term structures for homes, hospitals, schools, water storage and distribution, environmental protection, and more. Concrete is a crucial material for infrastructure, enabling wind farms, hydroelectric dams, and geothermal plants. In terms of energy, it's worth noting that concrete boasts the lowest embodied energy among building materials, which is quite relevant given that we are currently suffering from the discussion of energy shortage in New Zealand. However, since we use so much of it, absolute emissions accumulate to a notable amount. So as we adapt to climate change, we will use even more concrete for the reasons outlined above, but that has to be even more low carbon. So now we can switch on to the next slide. Fortunately, the cement and concrete industry is embracing this challenge head on. In 2021, the Global Cement and Concrete Association launched the industry's decarbonisation roadmap towards 2050, a global initiative that has received recognition from UN Secretary-General Antonio Guterres. Concrete New Zealand and our members are fully aligned with this roadmap. For Aotearoa New Zealand, the Net Zero Carbon Concrete Industry Roadmap to 2050 is a vital part of this global movement and, in fact, was one of the first national level responses to be launched. We will all have heard that the 2020s are crucial years, referred to as the decade to deliver. New Zealand's cement and concrete sector does deliver through accelerating CO2 reductions in cement and concrete production, leveraging all available technologies to drive further emissions reductions, implementing cost-effective measures such as improved building designs and smarter standards across the built environment, advocating for a clear, investable policy framework, including CO2 transport and storage infrastructure, and scaling up CCUS plants to enable mass deployment in the 2030s, 30s, and 40s, continuing to explore innovative solutions such as alternative cement chemistries and new heat sources. Our roadmap outlines the path to a 44% reduction in direct and electricity-related emissions by 2030 compared to 2020 levels, with a commitment to achieving net zero emissions by 2050. This ambitious target spans the entire supply chain without reliance on offsets. Now, Jeff, who has been instrumental in the development of this roadmap, will take us through the finer details. Thank you there.
Thank you, Tim. So what I wanted to do was to take you through the process by which we built the roadmap out. And so building on the work that the GCCA had done, we started out by saying, okay, well, what are the relevant parts of the cement and concrete life cycle that we need to be considering? So if you look at the life cycle of any product, you can look at it from a perspective of a cradle to grave or cradle to cradle, depending on how you want to look at it. This is a linear cradle to grave type view. Starting from raw materials, in the case of concrete, you're using limestone, which you then make into cement. And then the cement goes into making concrete when it's mixed together with aggregates and water and admixtures. And then that product goes into the construction of buildings or infrastructure. Then finally, the concrete is used. That potentially might be for a very, very long time. Looking at one of the examples that Tim had in one of his pictures there, might be for thousands of years, depending on what it is, or hundreds in a more human scale time frame. And then finally, once you decide that you need to get rid of an asset, it's how do we deconstruct it, demolish it, and then recover some of the materials there. So in the case of concrete, it might be crushing and recycling into aggregate. It might be the reuse of building elements that are still suitable for reuse, depending on their the condition at end of life. And if you break the manufacturing stage down further, you look at it mainly in two parts. There's cement manufacturing, which is where you start from raw materials like limestone or cement rock. You produce an intermediate compound called clinker. Clinker is then mixed with other minerals, often gypsum and limestone, to provide certain properties to the cement that you're trying to make. That cement is shipped out to concrete batching plants close to market, where it's mixed together with large, so fine and coarse aggregates, water, admixtures, to create a product that goes into an agitator truck, or is created directly on site to make a precast element, goes to the construction site, and then forms the buildings, bridges, and other concrete elements that we kind of know. The starting point for this work, as Tim mentioned, was really the GCCA's roadmap. So they'd done their own work in 2021. We were building off that and aiming to kind of contextualize it for New Zealand. And so they have a diagram that looks like this, and it talks about where they expect to achieve the savings at a global level, and how we plan to get to net zero. So if we're starting from 100% of emissions today, we factor in the idea that actually there's probably going to be some growth in construction between now and 2050. How do we then get that inflated number to account for future growth down to a number that is effectively zero? And the net zero part is just, we might need to have some ways of taking out CO2 because we can't reduce in an absolute level down to zero. And basically the way this diagram is structured is it kind of on the left-hand side shows some of the things we can do on the front end of the life cycle, and on the right-hand side it's talking about things we can do in the kind of more demand side. So if you look at the sort of top left, we can talk about savings in clinker production. So how can we change our thermal energy sources, use more alternative fuels, so exchange coal for biomass, for example, which is very topical in the New Zealand context. There's a bar here about efficiency in concrete production. How can we optimize our mix designs to take more of the cement out? Because when you're looking at the impact of concrete, typically speaking, about 80% of the carbon footprint comes from the cement. If you have mixed designs that have high, what are called SCMs, so supplementary cementitious materials to replace cement, then that number can come down. But generally speaking, it's the binder, the thing that's holding the concrete together, that is the high impact part of the life cycle. The aggregates that make up the bulk of the mass and the volume don't have quite as much impact because they're relatively easy to extract, in the sense you've just got a crushing process, or sometimes an explosive like blasting and crushing process to get them out. There are other things that you can look at here. Can we decarbonize the electricity grid? Can we look at recarbonation, which is a process that occurs naturally in concrete, which is absorbing CO2 out of the atmosphere? What can we do in terms of alternative binders, alternative replacements for cement? And then if you look on the right-hand side, you can see the two kind of biggest ticket items. The very far right one is really around design and construction. So how can we optimize the cement? How can we optimize the concrete itself to be right-sized for the project? So can we take more cement out? Do we really need that really, really ultra high strength concrete that is going to have more cement, more binder in it to achieve that? Do we need such early strength? Could we maybe delay that by the way we're using our testing regime, that kind of thing? If you look at the really, really big number, that's carbon capture, storage, and utilization. So how can we take carbon out and either store it or use it for some other useful purpose? And so with these sort of strategies in mind, with these ideas in mind, what we were aiming to do was to contextualize this. So in the context of New Zealand, for example, we've already got a relatively clean electricity grid. And so it was never likely that we were going to get to a 5% reduction off the back of electricity alone. As Tim pointed out before, concrete's not particularly electricity intensive. So that was probably going to be a non-starter right from the beginning of this project. And then you look at other things in terms of the use of supplementary cementitious materials. That's an area where we think we've got a lot more scope in New Zealand because we don't apparently use many, because we don't actually produce them in the New Zealand context. The common SCMs that are used internationally are things like fly ash and ground granulated blast furnace slag, neither of which we produce in any significant quantity or at all in the New Zealand context, so they have to be imported. And so we're starting from a kind of a lower base there in the New Zealand market. So what we did from that GCCA work is we identified a series of 7 strategies that we wanted to focus in on. Clinker, the first one, how do we reduce emissions from clinker production? So that's the first stage in cement production, and that is the most carbon intensive part of the current life cycle for cement and concrete. And so how can we use alternative materials? Can we use more biomass? Can we use alternative fuels to help bring that number down? The next point we wanted to look at was cement and binders. How can we reduce emissions from cement? Can we replace it with these supplementary cementitious materials, or SCMs? Can we add more limestone to replace cement? Can we use novel cement replacements, for example? The next stage was to look at concrete production itself. So once the cement's made, how do we make concrete in the most efficient way possible? How can we minimize the amount of binder that we're using, whether that's through the use of admixtures or different aggregate sources or central mixing plants or other things to kind of improve efficiency. The next lever was electricity. So how can we address decarbonisation and what will that mean? In the New Zealand context, we're looking at further decarbonising from an already fairly highly decarbonised base. Then we were looking more on the kind of sort of use and downstream side. So importantly, kind of design and construction. We wanted to consider in the New Zealand context, are we limited by our seismic requirements, for example? What does that mean in terms of what we can feasibly do in New Zealand? We wanted to look at carbon uptake, which is carbon storage from recarbonation that happens during the life of concrete. And finally, we wanted to look at the need for carbon capture, storage and utilization. So for what we can't take out in the first place, how can we take it out kind of after the fact or during the manufacturing process? And so when we came to do the analysis, we approached it in 2 different ways. And so as I mentioned, the starting point was the work that the GCCA, the Global Cement and Concrete Association, had already done. Their work focused on what we call Scope 1 and Scope 2 emissions. So it covered the direct emissions associated with cement and concrete manufacture, which is everything kind of going up the smokestack in your, out the flue in your operation. It's the direct emissions. It covers Scope 2, which is your electricity-related emissions, but those aren't particularly relevant for the cement and concrete sector. And we did this analysis using the GCCA's own calculator. They prepared a calculator tool, which was used for the global work, but it's also been used for a lot of other decarbonisation roadmaps in other countries. So there's one in Australia, there's others in Europe and North America. And so we wanted to align with the work that they'd done. So we were using their calculator for that part of it. But one of the things that came through from Concrete New Zealand's board is that it was really important for us to also consider the Scope 3, which is everything else. So that includes the stuff that's upstream that we'd otherwise ignore, but also the stuff that's downstream. So that'd be the transport of concrete from the batching plant to the site. It'd be the operating life of the concrete, and it'd also be end of life of the concrete. And so there was a clear steer from the Concrete New Zealand board that it would be good to include a secondary analysis, which we've called the EPD analysis, which also brings in Scope 3. So it's full Scope 1, Scope 2, and Scope 3 analysis, all of the emissions of concrete across this whole life cycle. And so we did 2 in this project. If you look at the roadmap, you'll see in the annex, the kind of scope 3 part, one of the challenges we have is just how to present 2 different sets of numbers. But we did 2 sets of analysis, and kind of we can cover both a little bit today. So just to make it clear what we're talking about when I say scope 1 and scope 2, and then also scope 3, the GCCA analysis, it covers the manufacture of cement, and it covers the manufacture of concrete from that cement. It also includes the indirect emissions from electricity, but it doesn't include the mining of the minerals that come in on the input side. It doesn't necessarily include all the transportation, and it doesn't include the downstream parts like transport of the concrete in an agitator truck to the site, end of life of the concrete, that kind of thing. And so those are the additional things that we wanted to build in. And the reason we're calling it EPD analysis is we were trying to make it at an equivalent level of what you'd see in an environmental product declaration, which is the format that a lot of the concrete industry around the world have chosen to use, along with many other industries, to communicate their carbon footprint, but also their broader environmental impacts. And so if you add in scope 3, we've effectively just snuck it in the gaps in between the bits here. The additional parts that we're including are the extraction of raw materials, the manufacture of the supplementary cementitious materials, which actually come from other industries. So fly ash being a waste product of the coal-fired power industry, for example. In New Zealand, the only source is the Huntly Power Station, and that often burns gas, so therefore doesn't produce fly ash when it's burning gas. So a lot of that material gets imported. Another common material is granulated blast furnace slag coming from the steel industry. In New Zealand, we do have a domestic steel manufacturer, New Zealand Steel, but they don't use a blast furnace, and so we don't have any domestic supply. So that has to be imported too. And now you've got in the New Zealand market, Holcim and HR Cement reporting that material. And then in between, we've got additional transportation to get cement to the batching plants. And then on the sort of tail end of the life cycle, we've got transportation to get the concrete to the site. We've got the whole life of the concrete, including the recarbonation that's happening during its life, where it's absorbing CO2 from the air. And then finally, we've got end of life, where it's potentially being crushed and reused. For example, crushed and recycled. Okay, so the process that we went through was we engaged with different member groups of Concrete New Zealand that Tim had on screen before. We brought in representatives of all the cement suppliers in New Zealand. We worked with the ready-mix concrete industry. We worked with precasters. We worked with the masonry industry. We worked with Concrete New Zealand's Learn Society to cover the demand side, so how that sort of demand side mitigation could work. And we also worked with the different sustainability managers across the different parts of the concrete industry to provide some view of a voice of the environment. I appreciate it's quite limited to the industry that we're in, but it was to give us something slightly different to the more production-oriented view of the world. And so what we found in the end is that in the New Zealand context, this is how we can get to net zero from a scope 1 and 2 perspective. So this is the GCCA analysis designed to align with the other global work that's been done. What we found is that we can get a 12% reduction in clinker, from clinker. Our biggest opportunity in the near term is around cement and binders. That's through the use of supplementary cementitious materials, through smarter design choices there. We can get a 9% reduction from the concrete production itself. We can get not very much from electricity because it's already pretty low carbon. So in the New Zealand context, we're only going to get to 1%. We felt that from a design and construction perspective, we couldn't get not quite as far as can be done internationally because we've got more seismic constraints about what we can actually do in our market practically. And then the stuff on the right-hand side, the carbon uptake, the carbon capture, utilization and storage, those are effectively exactly the same as the GCCA roadmap. We're effectively assuming that we can do the same amount that any other country can do on average in the New Zealand context. If we take that to be the full scope 3 analysis, what we call the EPD analysis, we get a slightly different way of representing it. This is looking at the same information, but over time. What you can see in the orange line, that's the baseline. We say here you've got GWP, ignore the terminology. GWP just stands for global warming potential. That's carbon footprint. So the baseline orange number here is the baseline carbon footprint of concrete. The green line is where we think we can deviate from that to decarbonize. But what you'll see is that this line, even with the stuff that we looked at from the GCCA analysis, where we're looking at decarbonizing scope 1 and 2 to net zero, so effectively zero emissions from the cement and concrete industry itself, we still don't get down to an absolute zero number here by 2050. And the reason for that is just that there is other things in the concrete life cycle. The concrete and cement industry are reliant on transportation of materials, so they're reliant on truck manufacturers, they're reliant on freight operators. They're reliant on the upstream raw materials that are coming in. So that's, your raw materials that you're mining, whether it's limestone for cement manufacture, but it's also those SCM materials that I mentioned, the alternative cement replacement materials. Those have a carbon footprint, and for them to decarbonize, we need the steel industry to decarbonize. We need changes in the coal industry to make that more acceptable from a kind of a climate change perspective. And so there are a lot of changes that need to take place outside of the cement and concrete industry itself. And so what this analysis is showing is, okay, yes, we've kind of got our existing picture. There have been improvements over time that have already happened, but we need to do more and go further to be able to get down to net zero from a scope 1 and 2 perspective, the direct and energy related emissions. To get down to a kind of a true zero, we need to work, and the concrete industry needs to work with all of the other industries that it's kind of part of. One thing I forgot to mention is this dotted line here is the concrete volume that we're looking at. We're forecasting an increase, and so we're looking here at achieving a net, like an absolute reduction, not just a reduction in intensity. We need to achieve a reduction also keeping in mind that there's probably going to be more concrete poured over time based on population growth and other factors. And so with that, I'll hand back to Tim, who can take us to what's happened since, and then we can take your questions. Over to you, Tim. You're muted.
Thank you, Jeff. Good. Picking up on where we were. So a key tool in tracking our journey to net zero is the annual Concrete New Zealand Sustainability Report, with the inaugural 2021-2022 report setting benchmarks across 5 areas: energy and CO2 emissions, freshwater usage, socioeconomic benefits, waste and circular economy, and workplace health and safety. The second report, due soon, will expand the scope and begin a time series, which is super helpful tracking these long-term factors and strategy outcomes. Foreshadowing the contents of the upcoming second installment of the Sustainability Report in 2023, we can already report a 6% reduction in direct and electricity-related emissions, despite increased production, moving us closer to the 44% emissions target by 2030. The gain is influenced by updated cement EPDs in line with NZS 3122, allowing more mineral additions without affecting performance, basically offering us supplementary ways to supplement cement within the base cement product or the default cement product. The use of supplementary cementitious materials has also risen from about 2.5% in the first report to about 4% in the upcoming one. This has been driven by continued investment in SCM supply infrastructure by cement suppliers, like the new slag mills commissioned by both Holcim and HR Cement in Auckland and Mount Maunganui respectively. In addition, we observe ready-to-use SCM imports through New Zealand Independent Cement, a sister company of Allied in the South Island. Last but definitely not least, in the low-carbon binder front, our locally produced Golden Bay cement is increasingly decarbonized through consecutive investments in increasing the share of alternative fuels in their cement, contributing to a circular economy through converting materials that dropped out of the cycle into useful energy. Transport emissions are also being tackled with new innovations like Firth's first fully electric ready-mix truck and 2 electric front-end loaders at Bullocks. And in addition, also, I think some hydro trucks from Golden Bay as well to deliver materials. So the transport emissions are already also in the focus. However, one challenge remains: the uptake of low-carbon concrete by specifiers like engineers and architects. This is largely due to limited experience with SCM effects on ready-mix and a lack of knowledge about how to correctly specify low-carbon concrete. We'll now take a closer look at both issues. Can you click? Yes, perfect. Due to time constraints, I can't dive too deeply into the technicalities of using SCMs in concrete. It's important to note that different SCMs behave differently, and just like virgin materials, there's variability depending on the source. The image on this slide shows the differences in shape and particle sizes of various binders, which clearly impact how they perform in practice. I've summarized some general effects of SCMs on ready-mix performance here. And while I won't go into full detail, your trusted ready-mix supplier can. They know their materials inside out and understand how specific mixes meet the needs of your projects. Now, I must address the elephant in the room. Set times for concrete with SCMs can be longer, particularly in colder conditions. While late strength is often higher, early strengths can sometimes be slower to develop. However, there are a couple of key points to keep in mind. First, this is primarily a logistical issue. Every building material, whether timber, steel, or concrete, impacts project timelines. Just schedule the difference. Second, the rest of the world, Australia, Europe, the US, has embraced SCMs in all applications. And third, as the author H.P. Lovecraft wrote in 1927, the oldest and strongest kind of fear is the fear of the unknown. Consequently, my final piece of advice is this. Whenever you are working on a project involving concrete, which is nearly every structure except a treehouse for your kids, refer to the Concrete New Zealand Plant Audit Scheme webpage to find nearby ready-mix plants. Speak to the suppliers about your project needs and let them tailor the mix to your requirements. Particularly for performance-critical projects like airport hangars or multi-story office buildings seeking to set benchmarks in terms of low emissions, consider asking them to prepare test cylinders in advance. I'm confident they'll be more than happy to collaborate. The amazing people I've met since my arrival in April are highly skilled and passionate about delivering sustainable solutions. Now, let's move on and talk about how to specify low-carbon concrete. With the wealth of information available online, and the capabilities of modern chatbots, some specifiers might be tempted to dictate precise mix designs to their concrete supplier. This could involve specifying exact percentages of SCMs, sourcing from specific locations, mandating a uniform carbon reduction target for all project concrete, or requiring a certain percentage of recycled materials. However, this approach can limit innovation, introduce unnecessary constraints, and create potential supply issues. Think of it like a visit to your GP. Medicine is a complex field, and it's usually best to describe your symptoms and let the doctor recommend a solution rather than requesting specific medications. Similarly, different healthcare professionals may approach your back pain differently. Whether it's a GP, an acupuncturist, or a psychotherapist, they use their expertise to offer the best treatment. As I mentioned earlier, concrete technology experts understand their materials inside and out. They consider your project's requirements, the distance from the plant to the site, and develop a mix that meets your performance needs using different tools to achieve the same outcome. It's great to see that low-carbon concrete specification is on the rise. Some engineering firms are now introducing general low-carbon concrete specifications that set a minimum global warming potential reduction for all concrete supplies, while still allowing for even greater reductions in specific areas of the project. Can we move on one slide, Jeff? In closing, I'd like to highlight the success of the Net Zero Carbon Concrete Industry Roadmap. It has effectively communicated a clear strategic vision, generated strong momentum across the cement and concrete sector, and equipped us with the tools to measure our progress towards the 2030 and 2050 targets. However, achieving these ambitions requires more than just intra-industry efforts. It depends on the wider building and construction ecosystem to actively demand sustainable materials and on regulators to provide supportive policy and economic frameworks. That's why we are thrilled to reflect on the progress of the past year, engage in this conversation, and collaborate with all stakeholders moving forward. Now, Jeff and I are happy to take any questions and hear your feedback. Thank you all for joining us today.
So we've had a couple of questions come in. I'm going to ask the first one here. Tim, this one's probably a Concrete New Zealand one, but I'm conscious you weren't involved at the time. So I'll ask it anyway. And then if you need to bounce it back to me, then feel free to. So questions from Rick, and it's what was your key learning from the roadmap process?
Now, as you said, I can't really talk to the process, but I can talk to the outcome. And the outcome is really that, I mean, wherever I go with different ready mixers, cement suppliers, they have all the same level of understanding in regards to what has to be done and what the levers are and where the whole industry has to move in the big picture terms. So that is absolutely positive. We don't see any quibbling or whatever different schools of thought in regards to trying to overturn or even resist kind of the movement. There's a clear positive momentum in regards to the identified levers, and that is a real helpful achievement of the roadmap, I would say.
Yeah. And from my perspective, being involved in it, I think one of the things that I realized is that there is a lot of ability to decarbonize now. It's just that sometimes the demand isn't there. And sometimes there's fear or uncertainty associated with doing something different, as Tim said before. And so part of this, I think a large part of this is kind of around education and all parts of the supply chain, right from suppliers through to the customers, working together to kind of collectively do something different and do something better than we've done before. And I think that's where, it is a collective thing. It's not just suppliers providing something. It also needs specifiers to specify it, clients to be willing to use it. When we're dealing with something new, there's always going to be that kind of change management thing that happens. And I think when you deal with buildings and infrastructure, there's always a bit of hesitancy to try something new because, hey, we've done it this way in the past and it worked well, and I think that's something that needs to be kind of tackled. And particularly as the scale increases, the costs of change decrease as well. So yes, the first project might be a bit more expensive. The next one will be cheaper. The next one will be cheaper, and you'll be at a point where you're cheaper than we were before potentially. And I think we just need to kind of go through that process, which other countries have already done, but particularly in the use of SCMs, but we haven't gone through yet in New Zealand. The next question is from an anonymous person saying, on a global scale, is there any benefit to importing SCMs? Or would these be used locally in the markets where they're produced if we didn't add to demand? Do you have any thoughts?
That's a tricky and important question, actually. I mean, in the global scale, obviously, the whole industry wants to move towards decarbonization. So we have a limited source of materials that we all basically serve ourselves with. On the other hand, I don't have the statistics of, not right now at hand, how much, for example, fly ash is currently being landfilled versus being used as a cement replacement. So given that there's certainly some cases where fly ash would otherwise be dumped and adding to environmental challenges, as opposed to being used in concrete, where it is basically stored in an inert way and basically permanently stored away, there's definitely some potential to improve the overall balance of material use. But again, it's kind of, that would require a truly deep analysis of the whole market. However, we only touched the so-called artificial SCMs today, since that's kind of the short-term solution that everyone is looking at. There's definitely some scope within New Zealand to look into the exploitation of natural pozzolans, so not dipping into industrial waste materials, but producing less carbon-intensive cement replacement materials from natural sources. And that would obviously then be a solution to that question.
Yeah, and that's actually what's modeled in the roadmap itself. We assume imported, waste product SCMs in the short term, and moving over the medium to long term to be using more and more domestically produced natural pozzolans as an alternative. So that's a good point. There's another question which is regarding carbon capture, storage, and utilization. Are there some good examples internationally where this is being done or being considered?
Yeah, I mean, that's the carbon capture, utilization, and storage is, I think, a thing that might be sometimes discussed in a controversial way. However, it is usually being discussed as a solution for fossil power generation to just extend the lifetime of fossil fuel power plants, which is absolutely not our intention here. We are talking about a natural and unavoidable component of conventional cement production, the CO2 emissions that occur when we convert limestone into clinker. And that obviously makes a much better use case from the point of view of alternatives that we have in order to decarbonize, as opposed to the energy application. And just giving a bit of a perspective in regards to scale, since we have only one local integrated cement producer in New Zealand, which is basically a single source or a single stack emitter, the application of CCUS would be a relatively easy thing to establish once there is a supportive regulatory scheme and maybe even the infrastructure to transport and sequester CO2. And the scale is really in the range of about 500,000 tons of CO2 per year. And looking internationally, there's currently one CCS site off the coast of Norway by the name of Snøhvit, which is operating since 2014 and is sequestering up to 700 something thousand tons of CO2 every year. So even a bit more than we would use for our entire New Zealand-based cement emissions component. So there is working references in the world in the same scale and size, and the safety is being monitored and tracked since 10 years now, and they are doing these leakage measurements every year and making sure that the safety is ensured, and we have very good positive responses from that side. And yeah, I would say that the scale and the particular cement application are real useful cases for CCUS.
Great. Next question is from Jürgen. What raw or recycled materials are in particular used overseas to make changes at scope 1, so for the direct emissions?
Yeah, I mean, in regards to raw materials, I mean, most of the emissions in concrete come from the cement production, or more precisely the clinker production, so replacing cement as a material or decarbonizing cement as a material, meaning decarbonizing the heat component and capturing the carbon, the chemical carbon. The alternatives are really looking into materials like calcined clay, looking into materials in the New Zealand context, for example, into pumice. There is use of pumice as a cement replacement in the US, in the southwest of the US. There are projects in regards to calcined clay in India, for example, that are going ahead. So that would be kind of the raw material part of the question, I guess. And recycling, the obvious recycling is crushing concrete into aggregate and then using crushed concrete as aggregate replacement, which makes sense. However, given that aggregate has a very low, natural aggregate has a very low emissions component, the real benefit or environmental benefit here is displacing virgin material and not so much the emissions component. Still, in a large urban center like Auckland or Christchurch, that absolutely makes sense to close the circular nature of the industry.
Yeah, thank you.
I mean, there's some international research projects looking into how to recycle even cement, make it reactive again, and use it again in the product. And definitely, I mean, New Zealand will probably not be the first country to adopt this, but is definitely an option for a fast follower.
Yeah. And if we were to do that, that would make a huge difference because of what you're replacing. Next question is from Paul. I understand that concrete made in Roman times absorbed large amounts of carbon over thousands of years. What's the difference with concrete made today?
Now, since the Romans used a lot of these pumice, so volcanic materials, to replace or to use alongside cement, I would say that probably the Roman concrete would have a lower carbonation potential than a concrete that is used with a high share of cement, like modern conventional cement. Because what really matters for the carbonation is the amount of unreacted or hydrated lime or calcium in the product. And I mean, the potential here is in fact large. The product category rule for concrete and concrete products provides some calculation formulas how to properly calculate carbonation, and the maximum carbonation after about 100 years of concrete in a landfill, or let's say maybe as a road base, would capture up to 75% of the clinker the free hydrated lime in the clinker over these 100 years. So that would, in numbers, that means basically that we can, per cubic meter of concrete, we can recapture about 100 kilograms of CO2 from the atmosphere over the course of 100 years of the building lifetime, another 100 years in landfill or as a road base. And in climate terms, which I mentioned in the beginning, that is quite relevant since CO2 has a lifetime in the atmosphere of several thousand years. So capturing back the emissions component from the cement CO2 release within 200 years is absolutely helpful in regards to mitigating climate change. Not in the short term, absolutely. I mean, we are releasing CO2 first, and it takes a good amount of time to capture it back. But in the time scale that climate change happens, it is absolutely relevant to consider that.
Thank you, Tim. That was our last question. I'm conscious we're over time, so thank you all for your attendance today. We really appreciate it. Thank you to Tim from Concrete New Zealand for dialing in today and presenting to you all. I wish you all a wonderful day. Thanks and goodbye.
We have many more webinar replays on a whole host of sustainability topics. You can check them out on our website and our YouTube channel.